My name is Ballin. I'm working in Professor David Wells' lab in the physics department. My project I built a radio frequency acoustic modulator driver, and I'll explain what all that means in a bit. Right. So we're a physics lab. Hot topic, or hot area of interest in physics, are condensed matter systems. An example of something like this superconductor. It's a material that has really exquisite properties and cool states of matter. Now these systems are extremely hard to study, and that's the problem because we want to know how they work. Luckily there's these other systems, namely ultra-cold atoms trapped in kind of a grid, that are much easier to study and behave pretty much the same way to these condensed matter systems. So we can perform experiments on these atomic systems and simulate what happens in the condensed matter systems to learn about them, how they work. Now, in order to establish this lattice of ultra-cold atoms, we use a lot of lasers. So we first have to cool the atoms. So the atoms come in really hot, traveling down a tube. Okay, I don't know why the animation isn't working. So the atoms come traveling down a tube. It's a really high temperature, and we shoot a beam at it in the opposite direction, which slows them down. And we also trap the atoms. So we establish a grid, like a grid of laser beams, and the cool down atoms come in and they get trapped in this beam, creating a grid. In order for these two processes to actually work, we need to be able to control the intensity and the frequency of the beam very precisely. We use something called an acoustic modulator, which is a box about this big. And we shoot a beam in through it down here, and depending on the signal we send to it, it will change how it affects the frequency or intensity of the beam. So here's a setup in our lab. Here's the AOM down here. Beams coming through here, hitting this mirror, and hitting this mirror, so you can see what happens to it. Now, as I said, how the AOM affects the beam depends on the signal we send to it. So to generate this signal, we use something called an AOM driver, which I'll be building. This generates some sinusoidal signal, which we can control the frequency of and amplitude of, and that gets sent to the AOM. And again, the frequency and amplitude of this will affect how it affects the beam. So when the signal is sent to the AOM, and you get this cool pattern. In this case, it's in each of these borders or dots next to it has a higher frequency than the one to the right of it. So these drivers are an existing technology, and you can buy them from manufacturers, but they're pretty bulky and expensive. And also, when we order it, it takes a long time for it to come to the lab, so we want to try to improve on that, which is my goal. So I'm trying to figure out how to build them cheaper, more space efficient, fitting them in these racks we have in the lab, and also developing an architecture so we can customize them to our needs. So you can kind of split up my project into two main parts. First part I call the internet shopping phase, where I scour the internet amassing parts. So that when I assemble them, they'll build the driver that functions as we want it to. But how do I know which part is good, which part won't work? I look at their data sheet, which is a list of the properties of each component. So for example, if I'm buying a power supply, I need to make sure that it can supply enough current to all the components in the chassis, which I will look at the data sheet to see if it can do that. The second phase is the assembly. Once I order all the parts, I first design the layout. So this is kind of a sneak peek ahead of the interface, but I have this kind of thing in mind. I want it to look like this. So I use this program. So I place holes that I want them to be drilled. Before I want them to be drilled out, it's a text on the front panel, and I send that to the company, and they machine that. And also, again, I want to make this device pretty space efficient. So I designed a layout for the internal components with the least possible spatial footprint. And then I machined the chassis. This they machined for me the front panel. I also took the rest of the box down to the machine shop and drilled out some holes and stuff. Then soldering some circuits together, and then screwed the components into the chassis. Here's some pictures of the final product. Here's a side view, a top view. Components are down here, a bunch of wiring. Right, and here's the interface. So we have dials, computer inputs, switches, and favorite part, LED indicators. So these indicators tell the user, is the computer controlling the device, or you can switch between allowing the computer to control the device or for manual operation via the dial. Now, for the results of my project, well, it works. Here's a graph taken using a frequency spectrum analyzer of the signal that it produces. So this basically plots the frequencies present in the signal that that the driver generates. So down here, just ambient noise. And here's the frequency of the signal I'm telling the driver to generate. And a byproduct of these devices, you get these things called harmonics, which can reduce, I guess, the efficiency of the AOM. And so we want these things to be as small as possible in comparison with the main signal we send out. So looking from the graph, we can tell that their intensity is 25 decibels less than the main signal, which is about 300 times. That's pretty good. Here's a graph showing power output of the driver as I change the frequency. These devices are perfect, so if I change the frequency, as you can see at the edges, the power level falls off. It's not meant to operate in that range. So the desired range of this specific driver is in this area, more like over here. As you can see, this is where it has the maximal power output, which is, we want more power. So what have I accomplished with this project? Well, I successfully reduced the cost by about 50%. And in the end, in the long run, we'll need about 30 drivers, maybe even more. That's $20,000. It's a good amount that we could use for other machinery. Also, each of these boxes represents kind of a layout where I can fit drivers for 3 additional components, which shows that I can make this thing pretty space efficient. 4 in a chassis, that's pretty good. Here's a top view of the chassis and one of the manufacturer's AM drivers. And there's no way you can fit 4 of these guys in here. So another point showing that it's space efficient. I've also been developing this wiki page for the lab. So what this documents the work that I've done in the lab, and also creates an architecture, meaning if a future lab member needs to build one of these drivers, they don't have to spend as much time shopping around the internet for all these parts. They can look on the wiki page and expedites the process. In the future, you can always improve upon the design. And also, I've noticed that some of the other labs on campus use these AOM drivers, so they may be interested in our architecture for cheaper, more space-efficient drivers. I'd like to thank my mentor, Zach Geiger, for teaching me a lot of cool things in physics and helping me along this process a lot. Dr. Lebedev and Professor Weld for letting me work in their lab and also giving me guidance. Also, EUREKA and Kevin for helping me develop this PowerPoint. Thank you.